addressing modeling and theory concerning AMO, and here we will see whether and how AMO may be preserved in ice core data. Here we are trying to show that ice core data, let us look at this lower portion of this figure. Here we have black line, which is limited in time, is AMO, basically from measurements, sea surface temperature measurements. Green line is AMO as reconstructed from 1650 on by Delworth and Mann, mostly from tree ring data. And red line, finally, is AMO. Basically, we have we suggest that AMO can be obtained. We take ice core data from 6 locations in Greenland and Canada, make average of the trended oxygen isotope value, and we believe that this averaging removes local or averages out at least up to some degree local influences, so that we are left with global influence, which we interpret as AMO signal. And this AMO signal is a red one. So you see it covers very nicely this instrumental epoch of AMO measurements, and in the past it follows reasonably well Delworth and Mann reconstruction of AMO. You also can notice that here from about 1920, this reconstruction of AMO by Delworth and Mann is not so good, because we have such a difference between black line, which is measurements really, and their reconstruction, while our oxygen 18 based AMO follow pretty well observed data. So this we basically provide as a justification that ice core can be used as a proxy for AMO. Here we show 600 years average of oxygen 18 ice core data, and this is average, moving average over the boxcar with a window of 31 years. And here is our spectral analysis of ice core data. So we have 600 years of ice core data, really 660. And we do spectral analysis of that average. And you see variety of peaks, or the simple periodogram has many peaks. But as we heard from Jerry North's lecture, we cannot interpret each peak being significant, and we have to use some kind of averaging. We use 11 years running filter, and basically result is our red curve. So you see that we have a 20 years peak, statistically significant. The only peak which survived is this 20-year peak. We have something like 40 to 50, which is much lower statistical significance. We say 20-year peak, but you see whether it is 18 or 20 or 22, it really depends on your analysis and cannot be exactly determined. So we have peak around 20 degrees. Why we started this work? You know that in 20th century we observed 60 to 70 year periodicity in the 20th century. So basically we said, let us look in ice core data and let us show that these 60 to 70 year peaks is persistent for several hundred years. Of course, you never find what you expect to find. So we did not find this peak to be really significant, but instead we find persistent this peak of 20 years. It was a big surprise to us, of course. But here is, wavelet analysis of the 600 years of data. So you see in this analysis, during the, from like 1800 till early 19, we have this peak here where we have a high concentration of power. So it is somewhere between 18 and 24 years in this analysis. But you see that this peak really exists, the 18th, maybe and 19th century. And if you go back in time, it does not appear there. Again, around 1650, and again here. So it is not really persistent peak which would be there decade by decade. It comes, lasts for 100 or 200 years, and disappears. And again, few hundred years, it comes back. So it looks like that really may be something which is excited by interaction of atmosphere with the ocean, and persists when it comes into existence, maybe for 100 or several hundred years, and again disappears. Here you see something, area outside of this curve is basically not statistically significant. But you see here in 20th century something which somehow suggests something with like 50, 60 years. And if you go back in time, you see it here, around 1600, you see clearly here, something between 40 to 60 years. So it looks like also that basically the ocean is kind of switching from 20 to 60 to 20 to 60, etc. So I believe ocean is a rather messy matter which decides to complicate our climate in a very unpleasant way, and it would be better if it would be forbidden. Okay. We have one I showed ice core data for 600 years. It was average of these 5 sites. Now we have one, which is dice 3, where we had 4,000 years of data. So here is wavelet analysis of this 4,000 years of one ice core. You see 20 years here again, clustered, for last 200 years. Then if you go back, you see something like, 60 to 70 years. Again, 20 years. About 50, 40, here you are back, to 20 and again to 60. So you see this switching between 60 dominant and 20 dominant goes on for, 1,000 years. Same thing is visible here. Here I have divided, this 4,000 year data into 1,000 year segments, and did a Fourier analysis on each of them. So you see, last 1,000 years shows you peak here 20. You don't see previous 1,000, you don't see it there, and you see it again only 4,000 years back. It shows you that it is dominant here in current millennium, and again 4,000 years back, for example. And in between, you don't see that 20-year peak. Then we said, let us look into in Greenland whether we see some differences between different regions. So instead of taking average of the ice core data of all ice cores, we divided it into South, Central, and North Greenland. And we process data separately, and what we find is the following. Dice 3 is South, it is here shown. So on dice 3 we see clearly only 20-year peak. In the central Greenland here, we see again 20-year peak, but here is something between 50 and 60, which is almost significant on 95% level. So, but when we go north here, we don't see any, neither 20 strong, we see something, but we don't see again 60. So it looks like the 20 years are clearly seen in southern and central Greenland, which somehow support idea that this is heat or flux basically coming from the Atlantic Ocean and basically is affecting this region here. The question is, of course, why in dye we don't see this 60-year peak. We really don't know, but we see it here in central Greenland only, which somehow again may suggest that really the 60 years may originate in interaction of Arctic Ocean with Atlantic. So this is, nothing is solved. We are just showing data, what data suggests. When I saw the Berkeley temperature project result, I basically immediately went to my file and dig out older file when I had this ice core derived AMO, and I sent it to Richard Miller, which superimposed it on his temperature data and sent it back. So it is sent to Richard Miller, and you see that you have really one-to-one correspondence in these 20-year peaks in Berkeley temperature project as well as in AMO signal as deduced from our data. I skip this since I will be running out of time. This is figure I showed in the introduction, so I will just mention one thing. It is decomposition. This is Arctic temperature, which we decompose into linear trend and this variability. What I want to point out, that if you look into Arctic warming from 1970 to now, about 1.2 degrees is due to this multidecadal variability, and remaining 1.2 degrees, roughly half, is due to some other effects. Obviously, it will be anthropogenic global warming plus long-term temperature increase coming from the last ice age. But 50% we see is due to multidecadal variability and 50% to something else. I just emphasize it here because it is what a few days ago Igor Polyakov obtained the same result from completely different set of data. So it corroborated that at least 50% of recent Arctic warming is due to multidecadal climate variability. Here I look how general circulation model can simulate Arctic temperature. So here I look specifically at Canadian CM Model 3, which was part of CENIP 3 project, basically models used for IPCC 2007. You see, black one is temperature observed. Individual wiggles up and down are individual simulations, in this case 5 simulations by Canadian model, and red is basically ensemble average. So you see that Canadian model, this one, cannot reproduce the peak in 1940, and basically is homogeneously, monotonically going up, and cannot reproduce this shape basically. I would like to say that none of 22 CENIP 3 model can reproduce this shape. None of them. Here is, for example, CCS and 3. Again, the same situation. They have zigzag going individual simulations A, but none of them really can reproduce this shape. Specifically, ensemble average does not reproduce that shape. Because of that, people decided that this peak in temperature here is due to internal variability of climate and cannot be reproduced by the models. Reason for that is, of course, the fact that models were unable to reproduce this peak. However, there are Canadian CENIP 5 models, 2 of them, just coupled atmosphere-ocean model, or Earth system model, which has built-in carbon cycle and vegetation. If you look into these models, you see that this up and down individual simulation goes up, down, and up. Same here. They go up, down, and up. And this shape is reproduced by each individual model simulation, as well as by ensemble average. It means that in Canadian models, new models for new IPCC 2013, this Arctic temperature is not natural climate variability anymore. Since it occurs in each individual simulation, it has to be forced. Now, people, how they change from CEMIC 3 to CEMIC 5 model, they change about 10 things at least together, including treatment of stratosphere, including ocean, including aerosols, etc. So basically, they have no idea what caused this, what is forcing that. And I doubt that they will ever learn, because it would require rerun all this simulation, which takes tremendous amount of computer time and tremendous amount of funds, which basically they don't have. So I keep it for you as a puzzle, basically, to figure out what forcing is causing, in Canadian models, this this drastic change, drastic improvement. Unfortunately, I don't have CCSM4 data. When I started to work, it was limited to members of the science team, so they did not give me data. I had to call Canadians who sent me data within a few days. So because of that, I'm showing you Canadian results, and I basically hope, there is a special issue of Journal of Climate, about 40 papers published on CCSM4, so I hope that one of those papers will, show really how CCSM4 reproduces or does not reproduces Arctic climate temperature. And my time is, I have still 10 seconds, which I will donate, for general. Oh, one here. Okay. I take it back, no donation. Okay, here is Canadian CCS, Canadian Climate Models 3. This is 20th century rate of temperature increase. Temperature of 20th century by individual simulation, by ensemble average compared to observed one. So you see, models over-predict warming by factor of 2 to 3. The same is true for CCSM, for Henk CCSM3 model. Overestimate warming by factor of 2 to 3. This is new Canadian model, this Earth system model 2. Individual simulation and observation. And you see they are almost perfectly on. Of course, their model was not tuned for Arctic. They tuned it as all other models for global temperature and global feature. And they basically are surprised, they are shocked how good their model is in Arctic. Thank you.
We have time for a couple of questions.
Chris Essex, UWO. I just wanted to comment on your remark about natural variability, and I just you used it in a way that I understand is quite normal when it comes to wanting to do ensemble averaging across initial conditions to cancel out kinds of transient sorts of things. But you could also imagine persistent kind of behaviors that are very persistent across different initial conditions, which are still part of the internal variability. They just happen to persist in that sense. So I just was wanting to point out this kind of alternative way of thinking of it.
But I fully agree with your comment. I am not statistician, so I do only undergraduate level of statistics. I understand that statistician can do much more, things which are much more complicated and less transparent.
In the CMIP5 simulations you showed, does the maximum temperature in the 20th century occur around 1940?
In simulations, no. Temperature, in 1940 we have a large peak in temperature, but still temperature in 2010 is still slightly higher than it was in 94, but it is just slightly higher. That is
Peter, do these simulations, obviously the data include effects of volcanoes, but they're smoothed over 11 years, right? So,
yeah,
so you probably smeared that all out.
they have all, these simulations have all 20th century forcings.
Okay, so the question I have is, can you unsmear them a bit and try to see if volcanoes have more effect in the Arctic than on the global average?
No, I don't have to show it. Volcano has no effect in Arctic. They are clearly visible on global temperature, but in the Arctic, maybe in some part of Arctic they may be like this. But if you take average over the Arctic, volcanoes are not significant.
Peter, I'm surprised you don't understand why the Canadian model does a better job. They're much closer to the Arctic than we are.
Well, you are right. If you take Ellesmere Island, they are north of Greenland. So they have to know, yes. Okay, thank you.